Well, up to this point, when we've talked about sampling or conversion of a signal from analog form to digital form, we've ignored a couple of important issues that take place in the A to D converter. A realistic A to D has both a limited amplitude range. In other words, it can't represent signals of arbitrary size. And of course, we're accustomed to that because amplifiers and so on have limited input ranges as well. The other thing about a realistic A to D is that it has a limited set of possible output values. And this is because we represent numbers that are being captured by the A to D in binary format so that we can get them in a computer. And if we have a limited number of bits, then there's a limited number of values that we can represent. So there's some sort of rounding or quantization that takes place. As an example, I have a digital camera, and the analog to digital converter in my digital camera has 14 bits of resolution. So this means that the color, actually it's either the red or the blue or the green because they have different colors for different pixels, but the color associated with a particular pixel can take on 2 raised to the 14th power possible amplitude values. We can sketch out the key ideas here if we break our A to D converter down into a series of blocks. We can think about this as starting with a continuous time signal x of t that also has continuous amplitude values. In other words, any amplitude is possible. Then we can think about a sample and hold operation that extracts the values of x of t at particular instants in time. So we've converted from continuous time to discrete time, and that's x of n. Now at this point, we're assuming that the amplitude x, the values that x can take on, are continuous. That is, any amplitude value is possible. So then our next operation will be a quantizer, which rounds the amplitudes to appropriate values so that now we have a discrete set of amplitudes that x can take on, and we'll call that xq. And then finally, the output of the A to D is usually in a binary format, and converting this discrete amplitude value into a binary symbol, that's a coding process. So we're going to talk about both the quantizer. The quantized output is the quantizer Q applied to x of n. And we're also going to talk a little bit about coding. So let's begin with the quantizer. And typically, quantizers that are used in signal processing have the following 3 properties that I've written out here. They're memoryless in that the quantized value at time n depends only on the input value at time n. In other words, past values of the input or future values don't affect the quantization process. Secondly, quantizers are usually a time invariant. In other words, the function that's doing the quantization, Q, does not change as time changes. It's the same at the first time instant as it is at the last time instant. And then thirdly, quantizers are generally uniform. And that means that there's a constant step size between the levels, and we'll explain that in a little more detail here. So what I'm going to do is sketch out the quantization function Q as an example. It might look something like this. Here I've assumed that the step size, or the size between levels, is delta. So my input x of n can lie anywhere on the horizontal axis. But the output that I get is one of a discrete set of values, some multiple of the step size delta. In this example, I've shown that the output is basically a rounded version of the input to the nearest step size. So for example, if the input to the quantizer x of n is between minus delta over 2 and plus delta over 2, we get 0 for the quantized output. On the other hand, if it's between delta over 2 and 3 delta over 2, we're going to get delta as an output. Okay, so we're rounding to the nearest level, what I've illustrated here. Now it turns out that this introduces 2 effects. One is that there's a possibility of overflow because the value x of n on the input side exceeds the maximum that we can represent on the output side. And that can be dealt with by properly scaling your input signal. And it's something we're not going to talk about much more. The other effect is that there's an error, a quantization error. We'll call that EQ of n, and that is the difference between the value to the input to the quantizer, which is the nominal true value, and the output of the quantizer. So that's the effect of rounding to these multiples of delta. And for this uniform quantizer, we're going to have that this error is always between minus delta over 2 and plus delta over 2. Okay, it has to lie in that interval for a quantizer such as I've shown here. We'll talk about characterizing quantization error in a separate presentation. So here's an example where I've shown the input as a continuous amplitude, continuous time signal, and then we're sampling. In this case, we're sampling at t equals 0.1 seconds. So I've got a sample at 0, at 0.1, 0.2, and so on. So we're discretizing time by sampling at those intervals. And then I've shown an example here where there's 5 possible levels for the output amplitude. The output amplitude could be 0, it could be 0.5 or 1, as well as it could be minus 0.5 and minus 1. You see that if I take this simple cosine and I evaluate at some point in time, the true amplitude is, say, here, and when I quantize it, I'm going to replace that with this amplitude. So I have an error, which is the distance between these two, and that's the quantization EQ. Obviously, the more levels we have, the smaller those errors are going to be, and we can talk about those effects, and we'll explain why CD quality audio is recorded with 16 bits and so on. There's reasons for that. So let's turn our attention now to coding. And we've got these different quantized values of the signal, and we have to assign a binary number to those. If you take computer engineering, there's lots of different binary representations, and ones that might be used could be such as 2's complement, sine magnitude, and so on. We're not going to go into detail on those sorts of number representations. But if I have a total of b plus 1 bits, then I can represent up to 2 raised to the b plus 1 quantization levels. If my range, that is the maximum value minus the minimum value that I'm willing to represent, is capital R, then my resolution or my step size can be related to the number of bits through this expression right here. So delta becomes the range divided by the number of quantization levels, or 2 to the b plus 1, and this again is for a uniform quantizer.